Okay, so what I've been doing is giving you motivations for thinking maybe there might be a space-time metric. What are the motivations? First of all, once you construct this table that we know we have, right? It kind of begs, and we know we have GI and we have GT, you know, you're saying, well, surely there's a G here, it's a four-dimensional metric. Okay, I mean, it's just a plausibility argument, it doesn't have to be, right? But you say, well, let me try to construct one and see what happens. And you construct one and you get this whole big thing here, and you find out in the right limit that you get gravity. Okay? Another plausibility argument for why this might exist. Remember we talked about phi, the gradient. The gradient was look for the steepest descent. What is steepest descent? If you think in terms of the potential function, and you're like descending a mountain, right? It means for any given, you have equipotential lines, right? You have these equipotential lines. From any given point, what you're going to look for is the thing that's kind of closest. What direction you go to get to the next equipotential line closest. That's the steepest descent on the mountain, right? Or the next level is closest, that's the steepest. All right, so there's something to do here with like the shortest distance between equipotential lines, which is kind of a property of metrics. You also know that the fact that there is this potential tells you that you can define energy conservation, which is a quantity that's path independent. However you go in this potential, whether you go like this, or like this, and end up here, or you move the thing like this, you've all done that path integral, and you find that your energy is the same at the end. The energy depends only on the endpoints. That's why it's such a useful method to use in solving problems, because it's independent of the path, it only depends on the endpoints. And that's, of course, also a property of metrics. The distance depends only on these 2 points, not on how you got there. So, but those are just kind of plausibility arguments. And again, it turns out you can't do this within Newtonian gravity, even within a space-time perspective. And when you try to do it fully, you end up with general. So what all this is a motivation for us to construct a four-dimensional space-time curvature theory with a metric. Not just a four-dimensional space-time theory with a connection and a Riemann curvature, but the very specific type of manifold which has more than just this structure on it. It has also the structure provided by a four-dimensional